Hi, ladies and gentlemen. Thank you all very much for coming to my presentation. My name is Xinyong Zhang, and I am from Renmin University of China. I have studied the topic of gaze-based interactions for more than 15 years. The title of my paper is Evaluating the Effects of Saccade Types and Directions on Eye-Pointing Tasks. This is the outline of my presentation. First, I will briefly introduce two theoretical evaluation tools as the background of my current work. One is the classic Fitts law, the other is the IDI model we previously proposed. Second, I will introduce the new 2D extension of the IDI model, making it able to be used in more general situations. Then, I will present our findings from two experiments. Finally, I will conclude my presentation. Fitts' law had been extensively used as a theoretical evaluation tool in the field of HCI, and it also can be used as a theoretical foundation to derive new models for other tasks. As the figure shows, the well-known form of Fitts' law in HCI is a Shannon-style equation, and it is able to accurately model direct or indirect hand-pointing tasks. Unfortunately, its effectiveness for eye-pointing tasks is doubtful. In our opinions, it is not suitable for eye-pointing tasks due to the underlying neural controls as well as the inherent features of eye movements. Thus, we specifically proposed a model for eye-pointing tasks, named IDI model, like this. In this model, the symbols lambda and mu are two empirical constants, reflecting the features of rapid and ballistic saccades and jittery fixations, respectively. This figure shows the speed of the eye cursor during a typical task trial, especially during the fixation on the target. The constant lambda is a very small decimal and mu is a measurable constant. Like the original Fitts law, however, the IDI model cannot be used to model the performance when acquiring rectangular 2D targets. Akkad and Zhai employed the methodology of weighted p-norm for 2D hand-pointing tasks. Inspired by their work, we also used this methodology to extend the original IDI model. The difference is that we use only one weighting parameter omega, instead of two independent ones, to capture the effects of the target dimensions. Now, I will describe the two experiments we carried out to verify the 2D extension and evaluate the effects of saccade directions and types. The left figure shows the devices and the experimental environment. The right figure depicts the interface of the experimental task. As can be seen, for each trial, at first the subject needed to look at the trial start button for a very short time to explicitly begin the trial by himself or herself. Thus, the target would immediately appear at the symmetrical position, and the subject had to fixate on the target as soon as possible. When the eye cursor had dwelt on the target continuously for 800 milliseconds, the target was successfully clicked. There are 12 saccade directions used to perform the tasks. In each of the directions, there were 12 combinations of saccade amplitude, target width, and target height. We defined three measures to evaluate the stability of the eye cursor and the human performance. The first one is average distance between the sampled cursor positions and their center, reflecting the degree of gaze noises. The second one is eye movement time. It denotes the moving time of the eye cursor from the start button to the target. And the third one is eye pointing time. It denotes the duration from the start of the trial to the moment when the target has been successfully clicked by dwelling. They are denoted using AD, EMT, and EPT respectively. As shown in the figures, saccade directions had significant main effects on these measures. The results of model fitting indicate that the new IDI model not only could be fit to EMT, but also to EPT. An interesting result is that the parameter omega appeared to periodically vary with saccade direction theta. In experiment 1, we only considered symmetrical saccades. In the second experiment, we additionally employed two different saccade types to perform the tasks. According to the primary position of the eyes, saccadic eye movements can be divided into centrifugal and centripetal saccades. The primary position is a natural constant position, and the eyes can be automatically reset to this position from any displacement of the visual line. For example, when we sit in front of a screen with our eyes straight ahead, our eyes are generally in their primary positions. This slide demonstrates the three saccade types. This demonstrates the directions used for centrifugal saccades. These directions are used for centripetal saccades. This presents the directions used for symmetrical saccades. The experimental results indicated that the factor of saccade type had significant effects on all the measures. The results of model fitting indicated that the extended IDI model was still able to accurately model the data in different situations. The regression lines clearly implied that centripetal saccades were better for eye-pointing tasks, especially when the tasks were increasingly difficult. The weighting parameter omega varied in different patterns, but with respect to symmetrical saccades, omega varied in a similar pattern to that in experiment 1. Here, I summarize the main findings in this study. The factor of saccade direction had significant effects on eye movement time and eye pointing time. The factor of saccade type also had significant effects on eye movement time and eye pointing time. The degree of gaze noises, AD, were also significantly affected by both factors. According to the weighting parameter omega, target height was more important in general to determine the task's difficulties. The tasks that were performed in horizontal or near horizontal directions, or the tasks that were performed using centripetal saccadic eye movements were able to achieve better performance. The extended IDI model could be fit to the data well enough. According to the results, we propose several recommendations for the designs of gaze input UI and experiments. Please read the paper for the details. Now, I conclude my work. In this study, we found that the Euclidean form of IDI was a suitable extension for 2D eye-pointing tasks, and it was more accurate than FITS ID to model the performance in eye-pointing tasks. The parameter omega can properly capture the asymmetrical impacts of target width and height. The IDI model also can be used in multimodal interactions when gaze input is used to move the cursor, because it was able to accurately predict eye movement time.